Welcome to the week 5 live session of Basic Linear Algebra. So first of all, to begin with, in the last session there was a doubt, there was a question from one of the persons saying that for all square matrix with full rank, the row space is same as column space. So there was a discussion going on this question. I would like to continue it and give a clarity on this question. So whether this is a true or false question. So first of all, when a square matrix is given, for example, let's for the sake of simplicity, let's deal with 3 by 3 matrix. So for example, if we are having a 3 by 3 matrix, square matrix, whose components are A, B, C, D, E, F, G, H, I. Okay, so now it is mentioned that it's a full rank matrix. Vishnu Sendil, could you please mute your mic? Some disturbance from your end. Vishnu Sendil, could you hear me? Yeah, thank you. Okay, so it's a full rank matrix. So what does it mean is it so what does that mean is we have the dimension of row space and column space both are going to be the equals to the size of the matrix. Okay, so what is the row space here is, so what is the row space here is, for example, if we, so these are the so this is what, row 1, row 2, row 3. So A, B, C, so these are vectors we have, and in the row space we can okay, so these are the basis for the row space, and I think, sorry, there's a disturbance from my end also, some construction work is going on around me. Okay, so so if we have any constants. Okay, so we have row vectors as A, B, C, D, E, F, and G, H, I, and row space is from the linear combination of these row vectors, and so this is the so this is a row space. So this is a row space. So if I'm able to prove that, I'm able to find alpha, beta, gamma, such that I'm going to get some elements here, which is equals to, which belongs to the column space. For example, the column space here is okay, so the column space here will be okay. So if I'm able to find alpha, beta, gamma such that I am getting some matrix in so I'm getting a matrix in the column space. Some values. So it can be either ADG or BEH, or maybe there's some linear combination of anything. So the stars can be, I just kept the stars here because it can be anything in the column basis. Okay, so now if I'm able to find alpha, beta, gamma, then that means that row space and column space are going to be same. Okay, so so the same thing I can write it like this. Okay, so I can write it like this. Okay, so basically this is just a transformation, this is just a transform of this matrix. Okay, so as it was mentioned that this is a full rank matrix, so this is also going to be a full rank matrix, because even determinant is going to be a non-zero for even this thing. If I'm expanding through this row, if I'm expanding here to this row, and here I'm expanding to this column here, so I'm going to get a I mean determinant will be non-zero. It's not non-singular. So easily I can, so some values I'm going to have here in column space, some values I'm going to have here, and easily I can, because this is full rank matrix, so I can easily I can get the inverse of this if I'm taking on either side. So so alpha, beta, gamma are unique here, so we can find any unique alpha, beta, gamma values for any vectors here in the column space. So because from the row space, from the linear combination of row space, we can also get any vector in the column space. So the row space and column space will be same. So this is a true statement. So this is a true statement. So all square matrix with full rank, the row space and column space will be same. Okay, so this was a question asked last time, and here's the answer. I hope it is clear now. Okay, so coming to the things which were discussed in the week 5 sessions, in the recorded sessions. So there are some so main topics of discussions were linear transformations and orthogonality. Okay, so we'll see the linear transformations and its properties. So it was discussed that for the linear transformations, the origin is going to be fixed. So if any transformation is there to the origin, then that is origin is not going to shift, and the collinearity principle will be applied, will be satisfied. So if you have a vector u, v, w, and you are applying some transformations, that you are getting tu, tv, and tw, and so if these are collinear, then even this transformation, after doing transformation, then still they will be in collinear. They will have the collinearity. Third thing which was discussed is if you have a vector u and v, v and w, and you have a vector u which divides these two vectors the ratio d, then even transformations of these vectors will be divided again by the transformation of u vector in the same proportion. So that is one more thing. And another thing is okay, the property anyways that is there. So linear combinations is equal to alpha of okay. So this property has to be satisfied for anything to be transformation, and also the transformation matrices for rotation, scaling, and reflections were also discussed in the class. And okay, so let's see some problems on this thing. So take down the first question. If you have a transformation from R2 to R3, and it is such that so tell me if T is a linear transformation or not. So for this question, the T is a linear transformation or not. So Atish joined now, right? So I think you were the person who were asking the question last time, no? All the square matrix
Yes,
with
yes, ma'am.
all the square matrix with full rank, the row space and is same as column space. Yeah, so
Yes,
you were
ma'am.
asking the question, so I just explained it now. So the answer is true. Okay, so in short, if I can explain it, it means that, for example, if I'm having a 3 by 3 matrix which is A, B, C, D, E, F and G, H, I, then because it is a full rank, I hope you can hear me, okay?
Yeah, ma'am.
Yeah, I think some disturbance in the background, okay? So A, B, C, D, E, F and G, H, I will be my basis because it's a full rank matrix, right? So it's my basis for the row space. So I can write it as a linear combination of the row vectors, saying alpha into first row plus beta into second row plus gamma into third row, okay, is equal to, I'm saying the star as here I'm giving some elements, the star here, which means that I'm getting it from the columns. For example, D, A, D, G is a column here, column vector. B, E, H is a column vector here, and C, H, I. So this can be here anything. For example, if I'm able to say that from the linear combination of the row vectors, if I can get anything, any vector in the column space, if I'm able to find alpha, beta, gamma, and using the row vectors, I can get vectors in the column space, then I can say that row space and column space both are going to be same. So here, for example, okay, so in this case, if I'm writing here like this, and the star can be anything. For example, this is a column vector, so it can be, for example, ADH or BEH or ADG or BEH or some linear combination of these three things. Then I can write this whole thing on the left side as this matrix ADH, BEH and ADG, BEH and CFI. So this matrix is nothing but the transformation of this matrix. So as is full rank matrix, so this also is going to be full rank matrix because determinant is not going to be 0 here, okay? So it's a full rank matrix and I want to find alpha, beta, gamma. So, and this is some vectors here in the column space. So I can easily, I can actually make the inverse of this and find alpha, beta, gamma, unique alpha, beta, gamma. So using row vectors, I can find the column vectors. So column vectors, vectors in the column space. So both the row space and column space are going to be the same. Okay, so this was discussed. So that was your doubt last time. I hope it's clear now.
Yes, ma'am. Thank you.
Okay. So now the question after that, the question, some linear transformation properties were discussed, and this is the question that transformation from R2 to R3 is there and is given like this. Then is a linear transformation or not? So let's solve the question. So as I said, the properties of the linear transformation is so if I have vectors given V2 and then this should satisfy. So ideally this should match. If that is satisfying, it means that this is a linear transformation. So it's alpha plus x1, alpha x1 plus beta y1, comma alpha y1 plus beta y2. So which means Okay, I made a mistake here. So this is the condition which was given. So the new vectors will be okay. So here it will be okay. So if you expand this, then if you compare this with this, I mean okay. Here's a simple expansion. So so this is the first component here. So you have the same thing. This will match with this, and this will second component will match with this, and third component will match with this. Okay, so the property is being satisfied here. So the given is a given T is a linear transformation. Okay, so I hope you understood this question. So next question is, if T is from R2 to R2 and T such that x plus 2 and y plus 3, so I am saying that this is a linear transformation. It's a true or false question. So T is a linear transformation. So it's true or false?
False, ma'am.
Yeah. Why so?
Origin is not preserved.
Pardon?
Origin is not fixed here.
Yeah. So yeah, that is there. And also, if you are doing this translation, I mean the linear combination property, even that is not going to satisfy. So so what does this actually mean? So what is this transformation look like? So this is actually a translation. I mean, if you have a point, if you have a somewhere point here, then just if you're adding it, like x is equal to. So you're just translating. Okay, so translation is not a linear transformation. So we have rotation, scaling, and reflection, all those things, they are linear transformation. All these things are linear transformation. But translation is not a linear transformation. Origin is not fixed, and even if you see this property, then it's not going to satisfy. Okay, take one more question. So if you have a point 1 2, P1 as 1 2, and point P2 as 4, 3. So rotate these points by 90 degrees and also scale by factor 2 and find the line of equation passing through this point, to the transform points. I hope my question is clear. So you have 2 points, 1 and 2, 4, 3. So you have these 2 points. So rotate it by 90 degrees and scale by factor 2, and you will get 2 new points. And what is the line equation through that? So this is rotation matrix. So new point will be for P1 will be this. So I hope you got this equation. 3x plus y plus 10 is equal to 0. Is it clear?
Ma'am,
Huh?
is the rotation matrix fixed, or we can switch the minus sign in sine theta?
I didn't get you.
The rotation matrix that you have taken is cos theta minus sine theta, cos theta.
Mm-hmm.
So my question is this rotation matrix fixed, or can we change the second row first position sign, minus sign?
If it is a plane, this is a fixed one. If it is a plane rotation, then it's going to be the same. This one.
All right, ma'am.
Is it clear? Okay. So one more thing which was discussed in the class was, once the values of linear transformation on the basis vectors are fixed, then it's fixed for every vector. It's fixed for every vector. So what it means is, okay. So let us see some examples for that. For example, if I have a vector v1 as 2 1 and vector v2 as 1 1. So I am doing some transformation on v1, that I am getting on transforming transforming v1 by t. I am getting new points as new vector as this, and on transforming vector 2 I am getting v2 as 1 comma 1. Then what is this transformation matrix? First of all, v1 v2 are they independent or dependent?
Independent.
Yeah, so they are linearly independent. So they can form a basis for a vector space.
Standard basis we want to take, ma'am.
Sorry?
Standard basis we want to take 1001.
Yeah, you can do that. Okay, let me
Uh, just one thing. I think Atish asked one question about that whether the rotation matrix is fixed or not.
yeah.
Whether that sine theta minus. I think it is fixed when we take it as a counterclockwise rotation. If we take clockwise rotation, automatically that minus sign will change.
Yeah, so if you are putting here as some minus theta,
Minus theta.
then,
Minus
yeah,
theta.
so
Yeah,
this
that
this
is
is
what.
not going to change. So this, yeah, so rotation.
Then cos theta, sin theta will come, and this side minus sin theta, cos
Yeah,
theta will
so
come.
yeah, so
Means
basically
for
matrix,
So
clockwise
matrix
rotation.
can be
orientation, it
kept
is
same.
about orientation. If we take
Exactly.
clockwise, then it
Exactly.
is like that. Yes. Okay.
Yeah.
If you
Thank
just
you.
keep
Yeah. Yeah.
Thank you.
rotation,
Okay.
rotation is like this. If you just want to change it to minus theta, then yeah, it will change.
Yeah.
So basically,
Yeah.
Okay.
you
Okay.
can remember this one.
Mm-hmm.
Okay.
Correct. Correct. Okay. Okay. Yeah.
Okay, I will solve this question. We'll take one more question on this. Okay, so as I said, so if I'm calling this as transformation, then I should be able to do this. This should be true. So I hope it's you are convinced till here. Okay, so what is v1 2 comma 1 and what is v2 1 comma 1? So transformation of 2 alpha plus beta alpha plus beta. Okay, and here if I see on the left hand side the alpha transformation I am getting as 3 comma 2 and plus beta transformation of v2 is 1 comma 1. So what I am going to get is 3 alpha plus beta comma 2 alpha plus beta. So for example, if I am saying this as x and this as y, then I can say 2 alpha plus beta is equal to x and alpha plus beta is equal to y. So if I what is alpha and beta here? In terms of x and y, alpha
X minus y it should be.
Okay, so alpha will be x minus y and beta will be 2y minus x. Okay, so now the same thing, if I am replacing alpha with x and y, then I can write like 3 into x minus y plus 2y minus x, comma 2 into x minus y plus 2y minus x. Okay, so it will be 2x minus y and x. So this is a transformation. Is it okay?
Yes, ma'am.
Okay, then we'll move on. Same, we'll do one more question on this. So I have vectors v2 and v1 as 3 comma 2 and 1 comma 2, and transformation I'm giving as then what is transformation matrix? Transformation is from R2 to R2. Okay, same one. So alpha and beta, you can get it like this. So so I hope you are able to get answer as x plus half y minus x plus 2y. So this value you are substituting as x and this as y, and when you solve for alpha and beta in terms of x and y, then this is going to become t of x. This is here it is going to become t of x comma y, and if you are substituting values for alpha and beta in terms of x and y here, then you will get the transformation txy. So this is the answer. Okay, so far we have discussed on the properties of linear transformations, like the origin is going to be fixed, and the linear combinations of transformation should be the property should be satisfied, and and also see what it means is, even here if you see, even this is the linearly independent. So even the previous questions which we saw, even here v1 v2 both are independent. So what it means is, if I am finding transformation values on the basis vectors, then for every vector in the vector space the transformation will be fixed. So once the values of transformation, linear transformation on the basis vectors are fixed, it means that its values for every vector in the vector space are fixed. So for every vector in the vector space, you have the same transformation. Okay. So we'll see about rank nullity theorem. So we have a linear transformation linear transformation from V vector space to W vector space. Then kernel of T means all the vectors in the vector space V such that the transformation of U will give you zero vector. So the size the size of all the U such that transformation of U will give you 0, that is called kernel, and range of T is
Set of images.
set of images. So whatever transformations you are doing and you are getting it on the vectors in the B vector space, B vector space, so that is going to give the range. Okay, and then dimension of kernel of T plus dimension of range of T is going to be equals to dimension of B. So this is domain, this is called domain, and this is called codomain. Okay, so basically, so kernel is subspace of
Domain.
Kernel is subspace of domain, and range is subspace of
Subspace of codomain.
Subspace of codomain, and dimension of kernel and dimension of range is going to give you dimension of domain. Okay, so based on this, let's see one question. Okay, so you are given a linear transformation. Okay, so you are given a linear transformation with dimension of range T as 3, then what is dimension of kernel?
It's 2.
Yeah, because dimension of kernel of T plus dimension of range of T is equal to dimension of R phi, right, range. So this is the domain. So this is domain, this is codomain. So phi, and I have given it's 3, and dimension of kernel, whatever it is, it will be 2. Okay. Okay. So if you are given a matrix, if you are given a 4 by 6 matrix, I mean, for example, if you are given a T matrix which is of size 4 by 6, and given the dimension of kernel is 3, then what is range? So if T is okay, tell me what is the range first, then we'll discuss.
Three, ma'am.
Huh? You're saying 3?
Three.
Sorry?
Yes.
Answer is 3?
Three, ma'am.
Yeah.
Yes,
so,
yes.
Yeah. So what is this 4 by 6 means? That T is going from R6 to R4. So dimension of range of T plus dimension of kernel is equal to 6, which means this will be 3, because I said this is 3. Okay. Okay, so one more question. So this is a true or false question. So a transformation T is such that R2 to R2 is from R2 to R2. So I am stating that a transformation T in R2 to R2 that preserves areas, also preserves lengths. So it's a true or false question. So if the transformation is preserving the area, it will also preserve the length of the vectors. True or false?
Is it false?
Okay, why do you say so?
If it preserves area, then length will change, no?
Okay, so
The length will either stretch or shrink if it preserves area.
okay, so for example, if I'm taking vector u, which is a comma b, and vector v, which is c comma d, then I want to find the area means what will I do? Determinant. No, determinant will give you area, right?
Yes.
So if I'm having a vector u and v, then this is going to give me area of parallelogram. Okay, so this will be the area we will be getting. Okay, so now if I, for example, if I am increasing the length of u and decreasing, if I'm doing it by if I'm doing it, for example, twice I'm doing, and if I'm making this as half, then even then it will become like 2a comma 2b and new vector, and this will become c by 2 and d by 2. So the area will be same if you are doing the if you're actually finding it, the area is going to be same, but the vectors lengths they got changed here, so this is a false. Yeah, so it's a false statement.
AD minus CB. AD minus CB by typo.
Yeah, thank you. I hope this is clear. Okay, now let's see one more question. So you have a derivative map from polynomial 3 to 3, which means on transformation, on derivative transformation, you're going to get, obviously you know that you'll get this. So what is the dimension of kernel for this transformation matrix?
N plus 1, so it would be 4.
Kernel?
Sorry, not kernel.
So basis for the v, basis for v is so this one, but the basis for transformed one is okay. yeah, that's a hint. Okay, so
Dimension is 1.
yeah, dimension of kernel is 1, right? That's right. Okay, so dimension of dimension here we have is 4, right? So dimension of kernel plus dimension of range is dimension of domain basically. So dimension of domain is 4 here because we have 4 bases here and we have 3 bases here. So dimension of kernel will be 1. Okay, I hope this is clear. Shall I move on to next question?
Ma'am, just a minute.
Ma'am, can we find its kernel?
Sorry,
Can we find its kernel?
in the sense,
Can we find its kernel?
can we find its kernel? Yes, you can find it. So
So what we will get? Only 0?
I didn't get you.
No, no, all the constants will be. All constants.
See, this thing you can like how you have here for we have already seen, no, in this, if you see this formula, you can relate to when we are solving the linear system of equations, then some this rank of the matrix plus n minus r is equal, nullity plus rank is equal to the dimension, the number of columns, right? We have already seen that. Could you hear me?
Ma'am, actually,
Yes, ma'am.
sir's question is how to find out the kernel of T. Like image T of P3 is equal to 0. So A1x set of all images, how to find out whose elements, whose images are 0. I think that he wanted to ask.
Elements means
How to find out kernel of T for this derivative map.
okay. Okay, I'll get back to it later. But what I can say right now here is, as we solve the linear equations, like we'll give the arbitrary values, right? Like for example, if we have 4 by 4 matrix and if we have rank of the matrix as 3, then we'll be having one nullity, and we'll be giving the arbitrary values for that. So in that way we can find, but we'll get back to it later.
Hello.
Yeah.
Can I try to answer this? Like I think just from the definition it will come. Like you have to just write u, where here u is the your vector a0 plus a1x plus a2x square plus a3x cube. Kernel means all such vectors u such that t of u equals to 0, right? So that t of u is going to be a1 plus 2a2x plus 3a3x square equals to 0. So where some equation like polynomial equation equals to 0 means here coefficients you have to calculate. Here you do not cannot calculate x. So one polynomial is equals to 0 polynomial means a1 0, a2 0, a3 0. So all those polynomials where a1, a2, a3 0, that means kernel will only contain a zeros, means arbitrary constants.
Yeah, so arbitrary constants, that's what. We'll get back to this doubt later, no? Because
Okay,
again,
sure.
if it is taking
Yeah.
time, then we'll
No
definitely get
problem,
back
no
to
problem.
this.
Sure.
Who is asking this question? May I know the name?
Ravi Shukla.
Ravi Shukla. Yes, I'll definitely answer this. Maybe in the last. Okay, let's move on to the next question. Okay. Okay, so this is the linear transformation. Such that where basis you can choose a standard itself. So basis you can take it as standard itself. Find this transformation matrix.
Is it 1, 2, 3, 4, 5, 6?
Yeah. So what will you do is we'll take the basis as standard basis as I said. So when you substitute, you are going to get 2, 4, and
2, 4,
6, and first column, for the first column you'll be getting as one of we'll take the linear combination basically. So again, so this is your first column, and the second column you can get it as so T you are going to get as okay.
Yes, ma'am.
So size, if you see, it will be like from here 3 by 2. take similar question. Real linear transformation such that and x minus y. So find basis 1 to basis 2 if basis 1 basis 2 is equal to standard and basis 1 is 1 comma 1 comma minus 1 and basis 2 is two questions with two different bases.
Answer to the first one is 2, 1, 1 minus 1. Ma'am, can you please show the previous page?
This one?
Yes, thank you, ma'am. This one. Second one. Done, ma'am.
Yeah. Okay. So this one is simple. So that will be 2 comma 4 and So I hope you got transformation matrix for first question.
Yes.
And to move on to the next question, then the basis is different.
T11
Yeah.
is 30. T1 minus 1 is 12.
So the first column will be linear combination you have to do, and second column will be again the linear combination. Of B. So you'll be getting here 6, comma 3. Okay, and here you'll be getting 0, 3. So yeah. Is it okay?
Ma'am, you have to represent 3 comma 0 in the form of the basis of B2.
Sorry, 3.
In the first column, you have multiplied 3 with 2 by 1, but I think 3 comma 0 should be represented in the form of as the linear combination of by using 2 comma 1 and 1 comma 1.
What is your question?
Ma'am, in calculation in the first column is correct. For the first column.
Okay, so you are
I
saying
think-
I made some mistake in the calculation.
No. My question is that, for example, T1 comma 1, 3 comma 0. So 3 comma 0 should be represented as the linear combination of the basis of B2, no?
Linear combination.
You are using as a-
how both are linearly independent, right?
Okay, ma'am, just reverse, just back the page, first page. Okay, ma'am, got it.
Yeah. Okay. Okay, another question. If you have transformations as so these are the transformations you have. So find transformation matrix for this.
No, I think I have a doubt. I think Ravi Shukla sir, what he was saying is correct. No, you have to write 3 0 in terms of as a linear combination of 2 1 and minus 1 1.
Yes, ma'am, that's my question.
What is the question? I didn't
Yeah,
get you.
3 0 you have to write. See, T of 1 1, the image of 1 1 is 3 comma 0. Then you have to write 3 comma 0 in terms of as a linear combination of the other basis vectors.
Yeah.
So you did not write, no? So that is what you have done in the first column equals to that. I did not understand first and second.
Okay, so you have did I write this wrong?
Yeah, because 3 comma 0 you have to write in terms of 2 comma 1 and minus 1 comma 1 as a linear combination.
Yes. So that's what done, no?
No. You are getting 6 comma 3, no, not 3 comma 0. You have to write 3 comma 0 as a linear combination of 2 1 and minus 1 1. Then whatever the coefficients I'm getting from that I have to write as a column.
See, basically whatever so first whatever basis you're starting, so this one see whatever values you are getting, you will write the basis of the codomain as a linear combination of what values you are getting here.
Basis of
So whatever
codomain.
basis, for
That
example,
is another basis you have
did you
given.
get the doubt in
B2.
the same question? The same thing we did here, no? The same thing whatever we did here, we did the same thing here. So 2 into
No, so other basis
0.
where we are using the other basis. We are not using B2, right?
No, we are using it, no? Yeah, B2. I told here B2 is this.
B2 is this.
Yeah, so
Then T of 1, 1, what is the image? T of 1, 1, that I have to write as a linear combination of.
T
Correct.
of 1, 1. Wait, 1 second. See, okay, let's see this. Is this question clear, first of all? First one. So T
First
of
one.
okay, so
Yeah.
T of 1, 0. In a basis 1, first of all we'll find in basis 1. So T of
So first one is
0,
clear because
yeah.
first one in both cases 1, 0, 0, 1. No, so it will
Yeah.
not make any change
Yeah,
actually.
so even B1, B2 both are 1, 0 and 0, 1. So we'll be writing as 2 here. We have 2 here. 2 as we like this a linear combination. 2 we use the coefficients. 2 into 1, 0, the basis of B2 plus 1 into 0, 1, the basis of B2 again. So we'll be getting
Correct.
this. Similarly this. So here now we are getting T of 1, 1. This one is correct, no? 3, 0, 1, 2.
3, 0 is correct. Yeah.
So 3 into basis. What is basis? I wrote 2 comma minus 1.
No. No, that you cannot do.
I wrote a calculation mistake. I think. Yeah, 2 minus. So and then minus 1 comma 1. Yeah. So I think this calculation mistake I made here.
Yeah. There is a calculation mistake.
Okay, so it will be 6 minus 3.
-3.
Yeah.
Still, it is not. It is not what you are doing, ma'am. Actually, there what you have done here you cannot repeat. So you have to write 3, 0 as a linear combination of the basis of codomain. Codomain basis is 2
Yeah, 2 comma minus 1.
-1. You are writing just the linear. Yeah. So 3, 0. See, ultimately, after the linear combination, you should get 3, 0. You should not get 6, minus 3.
Why will I get? I didn't understand. Like why I should.
So actually, ma'am, what you told. So what is the image? Like T of 1, 1, right? What is the image? You have to write this as a linear combination of the basis of codomain.
Yes.
This is not.
Yeah.
So whatever you are getting the image. So 3, 0 is the image. 3, 0 is the image. You have to write it as a linear combination of the basis of codomain.
Yeah. So
basis
this
of codomain is
codomain. So this is the basis of codomain.
Correct.
And I'm getting. So I'm writing it as a linear combination, right?
no, but you are getting 6, minus 3. No, you should get 3, 0.
We cannot get 3, 0 because the standard basis was 1001. This here
No.
we don't have
You
the
have to write
standard
it as a
basis.
linear combination. No. This is incorrect. So you have to write 3, 0 as alpha into 2, minus 1 plus beta into minus 1, 1. And from there you have to calculate what is alpha and beta is.
Okay. Okay. So we'll keep.
Even in video,
Yeah.
even in video examples, sir have discussed about the composition of two maps like S and T. So I think here the sir is not choosing the standard basis, so we are getting the correct answer actually.
Yeah, we are not having standard. We have two bases here. Two questions we have. I hope it's clear.
Yeah. First question is pretty clear. See,
Yeah, so
whatever.
second
So
question-
standard basis
Yeah,
image
see,
will
I
not
don't
change.
understand
Whatever
when,
you are getting.
Okay. So okay.
See, ma'am, just okay. Let's look at this page.
Yeah.
You see, for the first example, T of 1, 0 is 2, 1, right? And then 2, 1, you can write as 2 into 1, 0 plus 1 into 0, 1, right?
Yeah.
You are rewriting as a linear combination of the other basis, where other basis is the same as the previous basis, means standard basis. So see, 2, 1, you are writing as a linear combination of 1, 0 and 0, 1.
Yeah.
Now you go to the
We are
next
writing-
one.
we are writing
There you are
linear
writing
combination of
6,
these two.
minus 3 as a linear combination of the two. You should get 3, 0 as a linear combination of the other two.
Why should I get 3, 0?
Because that is the procedure. What is the image you are getting? You have to write this as a linear combination of the basis of codomain.
I don't think so. Okay, we'll keep this on hold first of all.
Yeah, okay. Sure.
Okay, so we have two questions here: how to find the kernel, and this one question. There's a doubt here. So basically,
Yeah, yeah.
what I understand is whatever procedure followed here, the same thing was done
No,
here
we
also.
cannot. No, we
So,
cannot. We have to write that as a linear combination.
we'll see.
Hmm.
Okay, moving on to next question. So this is a transformation you have. Yeah. So so first of all, find the transformation matrix, and also find the inverse transformation. Okay. So you can take the standard basis for this. If you take the both basis as standard basis, the calculation will be easier here. See, if here also, if you take B1 basis as this thing and even B2 basis as this thing, standard basis. So once you are getting T for the basis vectors, then you will be taking linear combination is the basis of B2. So it will be like again the same thing. So the first column here will be the same thing we were trying in the last time also, in the last question. And the second column will be we getting as? So for the transformation which was shown, so this will be the matrix. So if you want to find the inverse of the transformations, then you can find the inverse of directly. You can find the inverse of this matrix itself. So
Ma'am,
yeah.
may I tell you the answer? Is it correct? You please tell me.
Mm-hmm.
X1 is equal to 5y1 plus 3y2 minus 3y3.
Minus.
3y3.
Okay.
X2 is 3y1 plus 2y2 minus 2y3.
Okay.
And X3 is 2y1 minus y2 plus 2y3.
Yeah. So let me see. Let's see. So if you what is the determinant for this? Determinant will be, I think. So determinant is 1, right? So now we
Yes,
need to find
correct.
adjoint. Means for that, let's find the minor first. So minor will be okay. Then you have to find the cofactor matrix. So adjoint will be the transpose of the cofactor matrix by determinant. So we'll be having 5, 3, 2, 3, 2 minus 1 and 3 minus 2, 2 and determinant is in this one.
Ma'am, adjoint of a matrix, first row, last element should be minus 3.
Okay, I made a mistake in transpose. Which one you are saying?
In adjoint of T, first row, third element, it should be minus 3. 5, 3,
Okay.
minus 3. Rest of the things are correct.
I think just check it once. See, this will be okay. Okay, minus 3. Okay, so from this inverse, you can directly find x1 as sorry, to a minus 1. Yeah, so I think this matched. Yeah, so correct. Yeah. Is this okay? So if you want to
Yes.
find inverse of the so if you want to find the inverse transformations, means you just have to look into the matrix of it, and if you do the inverse, then you'll be getting the inverse transformations. Okay. So just take this is simple question. What is norm of this vector? Can I move to next question? This is the question. What is the norm of this vector?
Is it under root 56?
Yeah. So yeah, it's 56, under root of 56. Okay. So so if you have to orthogonalize this, how will you do?
Gram-Schmidt's orthogonalization process.
Yeah, so using this, find the orthogonal vectors. Okay, so calculation will go lengthy, I think so on this. So okay, so if you have this, so this is going to be you will start with this one. So k2 you will find it as 2 1 minus 3 minus of minus 3, and with respect to the first one you will remove it. So this should give you this will be so I hope you got this vector k2 as this. Now for third vector 3 3 3, you will remove the first one, dot product, okay. And then minus, so it's a big calculation basically, so, but I hope you understand how it goes. So did you reach till here? K2? Shall we proceed? Please skip this calculation. I think it will take time. So I hope you reach till here. Then in the same way you can do this also. Shall we move to the next question? Okay, take a simple question better. So okay. So find an orthonormal basis for the subspace of R3 the plane. So find the orthonormal basis for this plane.
Is it 1 by root 3 minus 1 by root 3 and 1 by root 3?
Were they saying only one? I think you should check on this again. Okay, so first of all, you have to find the basis. Then we can orthogonalize it, right? So you can start with finding basis. So this there's something which we are doing in the starting very beginning of the class. So we can write x by z as z. We have equations, so we can write as y minus z and y and z. So which we can write it as this way. So the basis we are having is this one. Now we have to orthogonalize it. So that orthonormal vector we have to find. So that is anyways the same thing as we have done before. So okay, so first of all, first thing. So first one, let us leave it this way. So K2 will be you have to remove its component. Okay, so this is orthogonal, so this is not orthonormal yet. So orthonormalizing means we have to divide by the norm of the vector. So we have and K2 will be hope you reached here. So did you get this?
Yes, ma'am.
Yeah. So yes. Okay. So here's a question for you. So if I'm giving you a basis.
Oh, so just 1 minute. Minus
We
1 by
do
root over
just see
6,
to
1
it.
by root over 6.
Minus 1 by
And
2,
the
1 by 2, 0.
Yeah.
No, what I'm saying, K2 is why the third term is 1. It has to be root over 2 by 3, no?
Yeah.
Minus 1 by root over 6, 1 by root over 6, then root over
Root 2 by.
Yeah, it's by both.
Uh-huh.
Yeah.
No, that is fine.
I'm sorry for that.
2 by root over. No, that is correct. Correct.
Okay, so one question here. So if the basis is already orthogonal, and if you are doing the Gram-Smith process for that, what will happen? So you are given a basis already which is orthogonal, and you are doing the Gram-Smith process. Then what you're going to get? Will you get the same thing, or will you get some other thing?
Same thing. We are going to get
Yeah,
same
so
thing.
there's no change. So basically when you're doing the whole process, there itself, because it's already orthogonal, you're not going to get any change there. So you're not subtracting anything there. Okay, so next, another true or false question. Okay, so Gram-Smith process, if you're doing for to a finite set, and that is not the basis of the space, that is not the basis. Of a given space, then what are you expecting to get? Like, what will happen if you are doing Gram-Smith process to a finite set of vectors which are not basis of the space? So it's not basis when I'm saying. So what are the vectors? What does that mean? It is linearly dependent or independent?
Linearly dependent.
Yeah, so linearly dependent, that is one case possible. So linearly dependent. So if you are doing Gram-Smith process to linearly dependent vectors, then which vectors you are going to get? Like, what can you hope if you are doing a Gram-Smith process to linearly dependent vectors? So here you'll be getting a zero vector. So when you are doing Gram-Smith process for linearly dependent vectors, you will end up with zero. It is 1 0 vector. Based on how many vectors are dependent. Okay, and then there is a possibility that suppose you have dimension of basis is 3, but I have given only 2 vectors, for example. Even then it is not making the complete basis of the entire space. Then what those 2 vectors will make? This will make the basis for the subspace. So if you are doing the Gram-Smith process for that, then you will be getting the orthonormal vector for the subspace of the given space. Am I clear? I hope I'm clear. Do anyone want me to repeat this?
No, like the second statement you made, it is clear, but how are you going to get the zero vector? Means that I am not clear about. Probably we have to prove. Like,
Yeah, we can.
like Gram-Smith process.
Yeah, yeah. So we can, if you take the example of some cases, so see, for example, if you are taking simple example, like you are doing similar thing, for example, okay, so or some linear multiple of that, then if you're doing Gram-Smith process, then anyways first vector you're going to have
We
the
are
same
going to
thing.
get zero.
Yes, and another thing, if you are going, then you just some both you'll be getting same, right?
Then
Yeah.
that is going to be zero
Yeah,
because
so definitely
yeah.
howsoever, I mean, like if you have n number of independent vectors, you'll be getting n zero vectors corresponding for that. I hope you understood.
Okay.
Okay, take a small question. That is, show that. Okay, so find projection transformation matrix for this. 40 is going from R2 to R2. So if any vector in R2, say for example x1, x2, if you are some vector, if you're projecting, suppose if you have some v vector, which is x1, x2 in R2 space, and you are projecting it on S, then what will be the transformation matrix for that projection? Okay, so projection means you're projecting on this vector. did you get this? So here you can take the basis, standard basis itself, right? For easier calculation. And the linear combination if you are taking, so you will be getting the first column. And second column will be so this is the matrix, projection matrix. I hope you got this. Is it clear? Is it clear? Any doubt in this?
No, ma'am.
So see, what I wanted to say here is, here we have taken basis as b1 also as 1 comma 0 0 standard basis, and here b2 also we took standard basis here. So once we substituted the basis values here, so we are getting the transformation of basis like this, and then we are doing linear combination with respect to basis 2. and then those will be the first for the first transformation we are doing if we are doing the linear combination, we are getting the first column, and for the transformation of second vector, if we are doing the linear transformation linear combination in terms of the other bases, then we are getting the second column. So I think even the same thing we did in this question. I think we had it out. Yeah. Shall we discuss on this now?
Yes, ma'am.
This question. See what we did here for the, so this question you all accepted, right? So this there was no problem in this. So what we did here is we just had a standard basis. So for the first basis of B1 we are finding as 2 comma minus 1, and for this we are finding the basis as we got a transformation of basis as 1 comma minus 1, right? And we'll be doing the linear combination for the basis 2. So this will be my first column for, and similarly this will be my second column. So what I'll get here is 2 comma minus 1, and here I'll be getting 1 comma minus 1. So this one everybody is convinced, right?
Yeah.
Yes, ma'am.
So same thing I'm following the same steps. Here I'm doing T of here 1 0 was the basis for the B1, so I am doing here as 1 1. So what should I get here? 3 and 0, right? And here I was doing for 0 1. Similarly same step here I'm doing here. So I'll be getting 1 and 2, right? Okay. So now with for this we'll take this as a coefficients, and we'll do the linear combinations for the basis 2 to get columns of the transformation matrix. So linear combination of basis 2 I have here, this 0 of minus 1 minus 1. Okay, so this will be my first column. And then now here for this vector, if basis of again basis will do means we'll be getting.
Yeah, actually, what you are doing, I think we have to see the definition of transformation matrix. It is like the image what I am getting, like in this case T of 1 1 is 3 comma 0, T of 1 comma minus 1 is 1 comma 2. The images what we are getting, that we have to write in terms of the another basis which is given. Whatever the coefficients are, that we have to present as a column. That is what the transformation matrix, the definition is. That is how it is formed.
Okay,
It is not like, so what you are doing here, like T of 1 is 3 comma 0. You are taking the linear, like 3 into 2 comma minus 1. So those things you are using as a coefficients. But actually it is not the case. The definition which I know,
okay. So
I
what
think
is
what,
what
yeah,
is
that is,
your final answer for this? We'll check in the next class. We'll already.
yeah,
Okay,
sure.
okay. So what is your answer?
Yeah, yeah.
What is your claim?
So, okay, wait, just let me, I have calculated. So, tell me the answer. I wrote it somewhere. Um, I think the first one is coming as 1 comma minus 1. 1 minus 1. And that second one I did not calculate. I have to see that. I'll do it. Because that time we were doing this process. Now I stopped actually.
Yeah.
So my claim is, I think we have to write 3 comma 0 as a linear combination of 2 comma minus 1 and minus 1 comma 1. Similarly, 1 comma 2 as a linear combination of 2 comma minus 1 and minus 1 comma 1. It's like that. That is what I think.
So what is the
That
final
is how
answer
we
you are
have to
saying?
do whatever. Yeah, final answer. Just let me give me just 1 minute. I'll finish it.
Yes. So it's already past 5. That's why I'll recheck again. I'll recheck once more.
No problem.
Is there any other question in assignments or anything? You can ask meanwhile. Whatever doubts in whatever we have discussed so far, or whatever in assignments, if you can tell me, I'll try to clear now or else in the next class. Anybody any doubts?
No, ma'am.
Okay.
Yeah, I think we are getting the same answer, like 1 comma minus 1, the first column. Second column is also 1 comma minus 1.
Okay, okay, we'll check
Yeah,
this.
sure.
We'll
Sure, sure.
check this and we'll get back to this in
Yeah.
next class. Okay, and one more
Yes,
question
no
was asked is the kernel part, right?
Yeah, yeah.
So we had a question like, I'll try to answer now. If you're not convinced, we can discuss in the next class also. So we had a derivative map. So from polynomial 3 to polynomial 3. So so this is same like what the same thing which you have seen, like dimension of kernel of t plus dimension of range of t is equals to dimension of the domain, right? The same like whatever we have, like rank of the matrix, plus nullity. Okay, so this inverse it. Nullity of matrix A plus rank of matrix A will be getting the number of columns, right? So here the same way, whatever we are doing to find the nullity of A, what we do is we go with Ax is equal to 0, right? Similarly for and then we'll solve for x, and then we'll be whatever we are getting, solution we are getting, that will say as nullity of A. Similarly, same thing we'll be doing for kernel also. So for example, if here we have so for this transformation matrix, way. If we solve this, whatever solution we are getting, that will be the kernel of, that will be kernel. Is that okay? Yeah, so I think Ravi Shukla sir asked the question and I think he gave a thumbs up, so I think it's clear for him. Any other doubts? Okay, so this part we'll just check. I'll check and get back to you later. And in case any doubts, please stay back. Else, see you in the next session. Thank you. Thank you so much for
Thank you.
participation.
Thank you so much, ma'am.
Thank you so much for the participation, the doubts you are asking, and the corrections you are giving. The participation, everything is a sincere appreciation from my end. I encourage it. For the lively session.
Thank you.
Thank you so much.
Thank you. Thank you. Thanks to you too for giving this much time. Thank you.
Yes, and patiently taking our doubts also. Thank you so much.
Yeah, thank you so much. See you in the next session.
Oh no, we can leave now, I think. I don't have any question. Thank you
Yeah.
once again.
Thank you.